Good afternoon, dear ladies and gentlemen. My name is Kamran Əliyev, and I recently completed master studies in the Faculty of Advanced Materials and Processes at Friedrich Alexander University. Today I would like to present my master thesis, the topic of which is the kinetic measurements and modeling of the partial oxidation of methanol to formaldehyde. Formaldehyde is in fact very important industrial chemical, and yearly more than 50 million tons of formaldehyde are produced. It's majorly generated through the Formox process, which is the selective oxidation of methanol over iron molybdenum oxide catalyst in the excess of air and temperatures between 250 and 400 degrees centigrade. Basically, in this process, heated air is mixed with methanol and introduced to the reactor. And as the reactions are highly exothermic, multitubular reactor is used for better temperature control. In fact, the performance of catalyst is quite good, and conversion is reaching up to 99%, and yield is reaching up to 94%. However, the major downside of this process is the short catalyst lifetime, which is associated with the deactivation of the catalyst. And catalyst deactivation is actually induced and accelerated by the hotspots, which are typically emerging in the fixed bed reactors, particularly in the case of highly exothermic reactions in my system. So in the given molybdenum oxide catalyst, molybdenum oxide phases are responsible for high selectivity towards formaldehyde. However, at high temperatures, these species do readily sublime from the surface, leaving behind iron oxide phases, which do readily catalyze complete oxidation of methanol to carbon dioxide. And it's important to note that selectivity is a vital parameter in the Formox process, as methanol accounts for 94% of the production costs. Therefore, the volatile molybdenum species are afterwards creating crystals, which also increase the pressure drop in the system. It means that basically by elimination of the hotspots, it could be possible to extend the lifetime of this process. However, for determination and possibly in the future elimination of the hotspots, one would need of reliable reaction kinetics. So the aim of my study is to develop kinetic model for the Formox process. In the next slides, I will briefly describe you the stages of the kinetic modeling. I could define the major principle of kinetic modeling with the famous statement of Albert Einstein: everything should be made as simple as possible, but not simpler. So the first stage of kinetic modeling is, of course, the collection of kinetic data. And for determination of intrinsic reaction kinetics, the selected reaction system should ensure adequate contact between adducts and catalyst. It should ensure the absence of mass and heat transfer restraints inside and outside catalyst, and also it should be possible to reliably describe the reactor characteristics at isothermal conditions, because kinetic modeling is typically done at isothermal conditions. In fact, a battery reactor could be considered as the preferred option, taking into account the requirements, because this reactor contains a high-speed turbine, which draws the feed gas several times through the catalyst bed, thereby facilitating ideal backmixing. And ideal backmixing allows us this assumption of a similar concentration inside of the reactor and in the outlet line. This means that the reaction rate can be simply calculated from the mass balance, exactly as it's typically done for continuous steel tank reactor. So I collected my kinetic data by simply varying the influencing variables such as temperature, pressure, inlet composition, and residence time. The next stage is the postulation of the reaction network, which can predict the reactions through which the products were formed. And accordingly, gas chromatography analysis of my product stream revealed the formation of formaldehyde, carbon monoxide, carbon dioxide, dimethyl ether, methyl formate, and dimethoxymethane. And the formation reactions of these products were identified by taking into consideration the available kinetic studies up to date. However, it is important to note that the majority of kinetic studies which were published up to date were carried out at temperatures lower than 290 degrees of centigrade, whereas the industrial process is typically conducted at temperatures higher than 300 degrees of centigrade. This means that one needs to develop kinetic model for higher temperature ranges so that the developed kinetic model is more relevant for industrial applicability. The next stage is the derivation of rate equations for the selected reactions using the available kinetic approaches. In fact, there are a lot of different kinetic approaches. However, the most important ones are Pavlov law approach, Hillary-Deal mechanism, Blackmore-Hinshelwood mechanism, and Marshall-Krever mechanism. The applicability of certain kinetic approach for the given reaction can be determined by tracking the dependence of the reaction rate on the partial pressure of the reactants. Or one can take this data from the available, let's say, past kinetic studies. For example, it is possible to see the difference between the dependencies of reaction rate on the partial pressure of different components versus the kinetic approaches which I provided here. In my study, I used Blackmore-Hinshelwood mechanism and Hillary-Deal mechanism. So, assuming that the absorbed gas in my system was ideal, I derived the following list of rate equations. I could name this like my final kinetic model, which I'm going to use to estimate unknown parameters. And unknown parameters here, as you can see, are the rate constants, and also the constants of Arrhenius equation, as you will see in the next slide. I assumed ideal gas conditions due to the fact that most of the experiments were carried out at low pressures and high temperatures. So the final stage, but the most difficult one, is the estimation of kinetic parameters. And as the kinetic model is highly nonlinear, one would need nonlinear optimization techniques like maximum likelihood formulation. In my study, I was using GPROM software, but one could also use a spin-casted modeler. It's also important to note that before rewriting all those equations in the software, it's important to reparameterize the equations to reduce their nonlinearity. And here I provide the example of reparameterization of well-known Arrhenius equation. So it was reparameterized in the given way. Finally, after parameter estimation, the results are viewed by contribution of parity plots, where the measured molar fluxes of components are plotted against the predicted molar fluxes of the component. And as you can see, the model predictions of the reactants like methanol and oxygen, as well as the target product formaldehyde, are very good, and the accuracy is of about 10%, whereas the model predictions of side products are within 20%. This is actually quite reasonable, particularly taking into account high exothermicity of my system. Lastly, it should be noted that my model has passed reliability check, which is typically done by contribution of significance analysis, statistical significance analysis. This means that my model can be potentially used to predict and generate temperature and concentration profiles, and this data is indispensable for identification of the place of the hotspots, as well as in the future their elimination. So this was the end of my presentation. I would like to thank all of you for your patience, attention, and I would be happy to answer to your questions, which you can address to my email address.